Good day, everyone. I'm so pleased to have another wonderful Friday with you, another webinar, and there were lots of registrations. Today, we have a very special guest, Dr. Anna Ennis, and she's from Waterloo University, or the Perimeter University, the Perimeter Institute. Sorry, the Perimeter Institute for Astrophysics in Waterloo on the east side of Canada. And Dr. Anna Ennis is more an experimentalist. She's a postdoc researcher and has a very interesting history because she originally comes from Argentina and has come to the cold of Canada in the east. Actually, her friend is Dr. Lisa Sarah. Oh God, help me with the name, Sarah.
Sassonova.
Thank you, Sassonova. That's right, Sassonova. I'm sorry for that. Lisa Satsonova, and she had been here talking about the evolution of galaxies in that, I think it was October 2022, so some time back, and she recommended you, so I'm very grateful for that. So Dr. Anna Ennis, welcome to iTelescope, and please go ahead.
Yeah, thank you for having me. It's really nice to be here. Lisa always spoke very highly of her experience here. She said that you were all a lovely audience, so I hope we'll have some fun.
We will, yes. So, do you want to share your screen and let me know when you want to when you run the polls and so on? Okay, it's completely up to you.
Okay, I might change you the order of the questions. So
that doesn't tuned. Just tell me what to launch. Okay, I'll pay.
Okay, that should be good. Okay, so as Christian said, I'm an observational astronomer. I work mostly on extragalactic astronomy. I've done most of my work on globular clusters, but I'm not going to tell you about globular clusters today, although I love chatting about them. So you can always look me up and contact me if you have questions about that. But I'm going to talk about my other line of work, which is related to stellar evolution. And we found this mysterious title, so I don't spoil it for you, but we're going to talk about the quiet giants. So we're going to talk about stellar evolution, and we're going to focus a little bit more on the end of the life of some stars that will not be as explosive as some of the more popular ones. So I would like to start with one of the questions from our poll, because I think one of the questions that I get asked very often when I talk about stellar evolution, or even when I just say that I'm an astronomer, is what's going to happen to our sun as it ends its life? Will the sun explode? So can we pull that one up and let people tell me what you think is going to happen? I'm sure you're all astronomy fans, so I'm sure we'll get some interesting responses.
1 second. Is that the one with Will the Sun Explode?
Yes, the first one.
That's the one. Yes, okay, got it. Okay.
Okay, so I'll start because it will take some time, but you have a minute to tell me what you think will happen to the sun as it ends its life. We know that a lot of stars do explode. So to talk about stellar evolution, the first step is obviously mentioning that stars do have a life cycle. So we know that stars are born and then they evolve and then they eventually come to what we very dramatically call their death, which is not technically a death, right? But when we talk about stellar evolution, we need to begin with how stars are born. So we know that stars are born in this type of environments, like this image that we've all seen here, because this is an image from the James Webb Telescope that was taken last year. It's an image of the Carina Nebula, and the Carina Nebula is one of many of the star-forming regions that we have in the Milky Way. So in star-forming regions like this, we see things like this. Okay, I get the answers from the poll. I will store them away. We have a high majority of hopefully nots and a few people that think it will explode. So let's see where the talk takes us in that sense. Okay, so stars are born. Stars are born in this sort of environments where we have these things that we see here that kind of look like mountains. Some people call them, there's the pillars of Earth. There's a lot of regions that you've probably seen if you're into looking at pictures of the sky, and they usually look like someone just got confused and took some sort of AI image of just mountains. But what we're actually looking at is big clouds of dust. So we see all of this in emission that is in the infrared, which is why the James Webb Telescope was able to take a really good picture of it, because in the infrared we can penetrate through the dust. We can see the emission in this very nice mountain shapes, but we can also see this sort of holes in the mountains. We see the sections that are very dark, and in the sections that are very dark, we see very, very bright points. So in these sections, what we have is a star that is being born. So we have a lot of emission that is pushing away at all of the dust, and the star is creating a cavity around it. So to summarize, what we tend to have is molecular clouds that collapse because of gravity. So we have a lot of dust in the shape of a cloud, and maybe some of those dust particles will collide into each other. And as we get slight overdensities, these overdensities will start attracting more and more of the material that surrounds them. And then eventually we'll get a big ball of material that we'll call a protostar. I will make a note of why we call this a protostar. It's basically a baby star, but we save the word star for things that can shine because of mechanisms that happen inside of them. Protostars are just balls of the material that we found in this cloud that are coming together because of gravity, and they are mainly made out of hydrogen, because that is the element that we have the most of in the universe. So 78% of the universe is hydrogen, so we have a lot of that to put together into our stars. When we have this ball of material that is coming together, it is being held by gravity. So the gravity that it's producing by its own power, just being mass that is constantly being accreted onto it, will eventually start to make this protostar want to collapse onto itself, right? Gravity will always want to pull things towards the center. So the star will accrete things on the outside, and eventually it will become a thing that can be held on its own by self-gravity, and it will want to just keep pushing and pushing everything together until it collapses. Luckily for us, protostars don't instantly collapse, because this process that gravity is making of trying to push atoms into one another will eventually cause them to fuse, and we'll get nuclear fusion. Nuclear fusion is the process that will make a star shine throughout most of its life, and it will keep a star from collapsing onto itself throughout, again, most of its life. The first process that's going to happen, because protostars and then stars are mostly made out of hydrogen, is a process in which this hydrogen gets turned into helium. So the stars will start to fuse the hydrogen in their more central parts, so in their cores. They will fuse it and make helium atoms. And in this process of nuclear fusion, a bunch of photons get released. And this is how stars start to shine. And that is the moment that a star releases its first photon out of nuclear fusion, is the moment that we decide that object can now be called properly a star. Depending on some properties of the star, they might go about this process in two different ways. There's two different types of cycles in which they can get their hydrogen to start becoming helium. And how they choose to do this initial process is part of what's going to determine the two big different paths that stars can go down on. So we had a protostar, now we have a star. We have an object that is shining because it's undergoing nuclear fusion in its core. It's turning its hydrogen into helium. And this is the part where we'll get two different options. And we are going to pull out a new question from the poll, which is question number 4, which is, what is the main characteristic of a star that is going to determine the course of its life? And I will give Christian a second. Amazing. So we have 3 options. Is it going to be the temperature of the star? Is it going to be the environment of the star? Or is it going to be the mass of the star? So I'll give you a minute to think about that one. We have basically two big paths that we know stars can undertake. And this is a bit of a tricky question, I'm not going to lie. Most of my questions are going to be a little tricky. There's never a clear answer in astronomy for things.
Yeah, I think we have a knowledgeable, from what I can see from the polls, I'll share with you in a moment. But I think people are paying attention. A lot of attention to what's going on. It's quite amazing.
I am not surprised. I expected this audience to be challenging for me, so
Okay, we'll wait a few more seconds and then.
yeah, give everyone time to click. Don't want to accidentally move to my next slide and spoil it.
Okay, 10 more seconds and then I'll share the results.
Okay, amazing. Okay, so as most of you know, the main thing that is going to determine the course of the life of a star is going to be its mass. Its temperature is sort of a tricky answer to put on there because the temperature of a star is connected. Like it's going to change throughout its evolution and it is connected to its mass, but it's not the main thing that is going to change the course of its life. The environment can have a very big impact on what the life of a star is going to look like, but it is definitely not the main one, especially not in these early stages that we're going to go through. So, as everyone here knows, if we have a star that is a massive star, so basically any star that is over 8 times the mass of the sun, what's going to happen is that after the star is done burning hydrogen into helium in its core, the core is just a core made entirely out of helium. It is not hot enough for the helium to start fusing into something else. So we just get left with a core that is starting to contract because of there's no nuclear fusion to push it back. So we just have self-gravity making the core contract. On the outside of the core, we have a shell that was made out of hydrogen. And because of this contraction, the outside shell of the core is heated up and it can start turning its hydrogen into helium. And then outside of the star, we have layers that will start to expand because contraction in the core will cause the outside to expand. And as things expand, they will start to cool down. This is a stage that we call a red supergiant. Red supergiants are really cool because they are some of the largest stars in the universe. They're not the brightest and they're not the most massive, but they are in size the largest. And we have a very famous red supergiant, which is Betelgeuse, as I'm sure you all know. And Betelgeuse makes my job of explaining red supergiants a lot easier because we all know a lot of things about what Betelgeuse has been up to the last couple of years. Red supergiants are very variable because they are very massive stars that are experiencing some fusion in their shells and they are expanding their layers. So they will change how bright they are. And they'll do things like Betelgeuse has been doing, where they will be brighter and then fainter and so on. But we also know what everyone's expecting Betelgeuse to do soon. So you kind of know what the fate of red supergiant is going to be. Eventually, this core that is contracting will become hot enough that it can start to fuse the next thing. So our little protostar turns star, now it's a red supergiant, and in its core, it eventually starts fusing the helium into carbon. And I know you're going to know the answer, but I will bring up now question number 5, because this is not the end of the core for a star that is this massive. This will go on to produce heavier and heavier elements. So I will ask you a question number 5, which is what is the heaviest element that can be formed inside of the core of a star? Now we're going to have a few options for that. There are a lot of heavy elements, and we do know, just keep in mind that we know that, as Carl Sagan said, we're made of stardust. All of the elements that we have in the periodic table are elements that came from stars somehow. But which one of them is the heaviest that we can form in this process of nuclear fusion that is happening in the core of a star? I'll give you a couple seconds to think.
Oh, we have a very knowledgeable audience. I don't understand why not more going so for supernovium, because that's the
I know you like supernovium. It's also a bit spoilerish, but we're not gonna pretend we don't know.
uh, oh, there are people voting for supernovium. I'm so happy.
Do it for Christian.
That's
It's
great.
such a good
Somebody
one.
voting. That's very nice. Okay, we'll just wait a few seconds and then we'll share.
Yeah. Okay. Another cool thing that happens while stars are doing this fusion in the core is that when we have a red supergiant, we have a star that gets larger, but it doesn't necessarily get hotter or brighter because it's not doing nuclear fusion in the core. But once it starts doing nuclear fusion in the core, it starts getting really hot and really bright really quick. And as most of you have replied, because you are a very knowledgeable audience indeed, this carbon will then be, we're going to start having a lot of nuclear fusion that was going to go down in shells. So we have outside, we usually tend to have hydrogen, then we have a shell made out of helium. We have our carbon shell, and this shell, which used to be the core, will start fusing into neon. The neon can fuse into oxygen, the oxygen can fuse into silicon, and finally the silicon can fuse into iron. Iron is the heaviest element that we can produce because the star cannot get hot enough, and there is a whole thing about quantum mechanics that will not let us go through nuclear fusion with iron. So once we get to iron, the star cannot keep fighting against self-gravity based on nuclear fusion because there's no more nuclear fusion that we can do. So for a while, the star will survive because instead of being held by nuclear fusion, it's going to be held by electron degeneracy. Electron degeneracy is based on the exclusion principle, which is a principle of quantum mechanics. So it applies to electrons because they're quantum particles. And basically it means that we cannot put two electrons in the same spot. The metaphor that people really like to use when they're explaining this is that if you go to a theater and all of the seats are full, then you cannot really sit anywhere. So you have to either leave or kick someone out. Electrons cannot really kick each other out of the spot they're in, but because they just cannot keep being compressed. They cannot hold, they cannot just melt into one. So they will fight back against self-gravity for a while, just because they're trying not to get pushed against each other so much. But electron degeneracy can only hold up to a certain level of self-gravity. So because the core is trying to collapse and it's getting hotter, electron degeneracy at one point will just fail. And then the star will succumb to self-gravity and it will explode as a supernova. These are not the quiet giants. Supernovae are not quiet at all. They are loud and bright. They're also stars that are have very short lives. I say this as an astronomer, I realize a million years is a long time, but in astronomical times, the lifespan of a very massive star, such as this one, takes about 25 million years. And that is very short in the terms of what we think of when we think of astronomical timescales. But we don't really care about the massive stars. Everyone likes supernovae, but I'm a defender of the low mass stars. So if we have a low mass star, like our sun, which is a good reason to care about low mass stars, we call low mass anything that is less than 8 times the mass of the sun. The process will start kind of similar. So we had our star, it was burning hydrogen into helium in its core. Eventually, it runs out of hydrogen. It has a core which is made of helium. This core starts to contract. The shell outside starts turning hydrogen into helium, and the layers start to expand. Everything's kind of the same, except these stars are less massive and less hot and less big, less large than the red supergiants. So because astronomers are so good at putting names on things, we call them red giants, so that no one gets confused. One very bright red giant that we have in our sky that is very easy to look at is Aldebaran. Aldebaran is right there. It's very easy to see it with the naked eye because red giants are very bright and they are very red. So our sun is, right now, it's doing his whole turning hydrogen to helium in the core. In a long time, it will turn into a red giant. It's going to start to expand. The layers will start to cool down and it's going to turn really red. Eventually, the core contracts enough that it heats up and it can turn this helium into carbon. And in the case of low mass stars, this is all the core can do. It turns its helium into carbon and then it's done because it's not massive enough to heat up enough to turn the carbon into anything else. So we're kind of stuck with usually a carbon. Maybe there's some oxygen, but it doesn't get further than that. This is, however, a bright hot star that we have while it's doing this process. And then after it's done and we have a carbon core, we kind of have a similar situation to what we had before. We have a core that's contracting because it doesn't have nuclear fusion pushing out water anymore. It has a shell that's turning helium into carbon, and then it has an outer shell that's still turning some hydrogen into helium. And then there's these big envelopes that are moving away. This phase is called the asymptotic giant branch, which I think is one of the least pretty names that we have in astronomy by far. It has to do with how we understand the path of a star when we think about its brightness and its temperature, but we don't really care. We tend to just call them AGVs because no one wants to say all these very long words. And AGVs are actually really cool because while they are doing all of this, because there's so many processes happening all at once, we have so many shells and we have the envelope and there's so many materials and the temperatures are so different, we have what we call thermal pulses. So the star will expand and contract and expand and contract because all of this shell fusion is causing it to change temperatures. And at the same time, we have this very, very hot core that is emitting radiation. So it's emitting very high energy photons. And these photons cause what we call winds. So there's a lot of radiation pressure that's coming from these high energy photons that come from the core that is also pushing away this envelope and heating it up. After stars go through the asymptotic giant branch, because we cannot keep doing anything, the core is done. Its job has finished. It's just made out of carbon and it cannot keep doing nuclear fusion. The shells will eventually run out and they will no longer be able to fuse anything into anything else. We kind of will end up with this envelope that is slowly being torn away from the core. And that is what we call a planetary nebula. So planetary nebulae are some of the best looking objects in the universe, but they are also some of the ones with the most confusing name ever. The reason for this really weird name the planetary nebulae have, I think the one at fault is this nebula in particular, which is the Saturn nebula. So people had seen planetary nebulae before. There's evidence of planetary nebulae even in the early 1700s, people looking at the sky and being like, there's this pretty object. I'm not really sure what it is. You have to consider that in the early 1700s, people were also thinking that everything kind of looked like a nebula to them. Galaxies were called nebulae. Everything that looked a little blurry and was not like a proper pointy star was called a nebula and just kind of left as a confusing item. But in 1780 something, William Herschel was looking through his telescope and saw this particular nebula. And he thought this looked a lot like Saturn, which I think it isn't fair of us to look at this Hubble image of the Saturn nebula, because this is not what Herschel looked at. What Herschel looked at looked something like this. So if you see this, you can kind of see why he thought it looked like Saturn, because it very much looks like you have something round and then there's something that kind of looks like a disk around it. So he was like, maybe this is a planet that's forming. He was not very sure. He kind of gave it the name planetary nebula just to say something. And then people went on looking for this weird object and found some of the most classical ones. They found very early on the Dumbbell Nebula, which is very straightforwardly named because it very much looks like something you would use to do weights at the gym. They found the Ring Nebula. You can see they were not really being creative with the names. I like the Ring Nebula a lot because I feel like when you stare at it, it kind of looks like it's staring back at us, which can be fun or creepy, depending on how you look at it. But the information that we have of how this planetary nebula name came to be comes mainly from this letter that Herschel wrote to his friend Jerome in 1785, where he says, I am writing this paper where I'm listing the coordinates of half a dozen planetary nebulae, as I call them. He just says these are celestial bodies, which we have no clear idea and are perhaps of a type quite different from those that we are familiar with in the heavens. So he kind of said what size they had, what colors they had. He said they appear to have a disk that is rather like a planet. So it's not like Herschel said these are planets, but people really liked this name and ran with it. And we now know that planetary nebulae have absolutely nothing to do with planets. But we are, I guess, too lazy to change the name. It's been, what, like 300 years, might as well leave it. After Herschel named the nebula, a lot of people went on looking for them. They took a lot of pictures. You can find a lot of ancient images of nebulae. But it would take another 100 years for someone to finally understand what it was exactly that we were looking at when we look at them. And the nebula that brought us an understanding of what planetary nebulae are is this one, which is the Cat's Eye Nebula. So 100 years after Herschel, William Huggins, who was an astronomer in London, looked at the Cat's Eye Nebula, and he didn't just have a telescope to take pictures with, but he had a prism, which he used to disperse the light of the nebula. This was something that people were already doing quite a lot in the 1800s, and they kind of knew what they expected from the spectra of a star. So when you disperse the light that you get from a star, usually you get something like this. In these examples, we have Vega on top and Aldebaran on the bottom, and the proper spectra is the bright line that we see in the middle of each of these images. So what we tend to get when we look at the spectra of a star, I mean, we're getting all of the light of the star, and we're dispersing it across the entire wavelength range that we can cover. So we see a bright band because the star is emitting light in most frequencies. It's emitting light in all frequencies, right? So we see all of this very, very bright band that we call the continuum, and then we see all of this dark lines that you see vertically on top of it. And these are absorption lines because the star is usually shining from its core, and then it has an atmosphere, it has some sort of envelope that has some elements in it, and the elements in the envelope will absorb some of that radiation. So when we look at the spectra, we get the continuum, the absorption lines, and sometimes we'll get some emission lines. If the star is of a specific time, maybe that some of those elements in the envelope are actually taking the light, recombining, and then re-emitting the light. So this is what he was hoping to see if planetary nebulae were stars, or even if they were galaxies, because we know that galaxies are made of stars. So we get things very similar to this. What Huggins found instead was very different. When he looked at the spectra of the planetary nebulae, the Cat's Eye, he found nothing for the most part, and he found some very, very bright emission lines. He found some hydrogen emission lines. There's specifically an H-alpha that's very bright, and he found a very, very bright emission line in a place where there was no record of any experimental emission line. So there was no emission line that could be made in labs that matched the place at which he found this line. Huggins was confused about this line. He didn't overthink it too much. Initially, he thought it was nitrogen, which is why he called it N. And then eventually some people would say that this could not be nitrogen because we know that nitrogen does not leave a line in that part of the spectra. So they decided it was a brand new element that should be called nebulium after the planetary nebulae. When Huggins writes about his discovery, he says, "I looked into the spectroscope, no spectrum such as I expected, a single bright line only. This is how I feel when I look at planetary nebulae as well." But Huggins was very smart, and he said, "At first I thought maybe I'd done something wrong, there was some displacement of the prism, and then the true interpretation flashed upon me. The light of the nebula was monochromatic, the radial of the nebulae was salt." So what Huggins realizes is that the nebula seems to be shining in very specific parts of the spectrum. Instead of giving us a continuum like most stars, something is happening to the nebula where it seems to just be shining. You can see nebula if you look at very narrow band filters. Like if you put a narrow band filter in your telescope at specific lines, you will see the nebula really, really bright. And if you put a continuum filter, you will miss the nebula. So something was going on. He was content with saying that it was monochromatic and moved on from that. But now we kind of understand planetary nebulae. Thankfully, we don't fully understand them because that is the reason that I have a job, but we understand more than we did in the 1800s. So when we have our asymptotic giant branch star, which we talked about before, we have our core that's made of carbon and oxygen, our shells that are doing fusion, and then we have this envelope that is very rich in hydrogen. And at the start, Because this envelope is very hot in the parts that are closer to the shells and very cold in the outside, it is working the way that we call convective. So there's convection happening in the envelope. Convection is the way in which heat is distributed across a material in general. So we talk, an easy example of what convection looks like is if you think about boiling water in a pot, you'll have very hot water at the bottom and colder water on the top, and the hot water will rise and the cold water will go down, and this is how water gets heated up evenly throughout the pot. This is sort of what's happening here. So the material will go up and down depending on how hot it is so that it keeps getting evenly heated up. In order to have convection, we need some parts of the star to be way hotter than some other parts. But because of convection, at some point this won't be true anymore. Heat will be distributed more evenly, and the star will go from a convection mechanism to the radiation mechanism. And in a radiation mechanism, we just have photons running out of the star and heating up the star in a very normal way, like we have throughout most of the phases of the star. So when we talk about AGV stars, we talk about stars where energy is primarily transported through the motion of hot gases. And when we talk about post-AGV stars, we talk about stars where this happens mainly because of photons. Photons can move freely through the envelope and they can carry energy. So our star went from convection to radiation, and in this process, a lot of things that are happening to the temperature of the star are getting complicated. So as we go through this post-asymptotic giant branch phase, this envelope, because it's radiated now, it starts to contract. The radius of the star goes from 200 times the radius of the sun to 3 times the radius of the sun. So we have this envelope that is cooling down, and it is being affected by the central star. When we start to reach the planetary nebula phase, we have a very hot central star because it's still hot. It did a lot of work. That poor core turned all of its helium into carbon, and it still has a lot of thermal radiation. So it has UV radiation that's going out of the hot central star. There's a lot of winds because we have all of these shells, and we have all of these high energy photons that are going out of the star, and we have super winds that are caused by this change in the mechanism. And around the star, the envelope is made of very, very low density material. So the main mechanism through which planetary nebulae give us this really weird spectrum that we see is the combination of two things. On the one hand, this very low density material is being ionized because it is receiving all of this UV radiation that is heating it up. The electrons from the atoms that make up this material are getting ripped from their original atoms, and this process emits photons. So what happens is, if we look at a star, a normal star, so if you look at a star at any other phase, we'll mostly see the spectra of the hot central star and how those photons come to us. Because here we have this envelope that's also emitting thermally, the continuum gets very blurred out, and we get a very flat continuum instead of the continuum that we would get from a star that didn't have this envelope. As these electrons are stripped from their atoms, they recombine with other atoms, and the process of recombination is what emits the photons that make up the emission lines. In particular, the line that Huggins saw in the 1800s and that we still use to find planetary nebulae today does not correspond to an element called nebulium, because there's obviously no element called nebulium that we know about. But what was happening is that the processes that we see in places like the envelope of planetary nebulae are very hard to reproduce in labs on Earth, because what's happening here is happening at a level of low density that we cannot really reach in our human conditions. So the lines that we see in planetary nebulae are what we call forbidden lines. These forbidden lines, in particular the line that was called nebulium, is what we call the forbidden oxygen-3 line. This is a line that requires atoms to be far enough away from each other that when an electron is placed in a specific level, it can stay in that level long enough for it to eventually just drop to the level before it and release that one line that we saw. In normal conditions or in the densities that we can reach on Earth, this never happens because we cannot make materials be at a density low enough that the element doesn't get hit by something else and emits a different line. In the very low density cloud that we have around the nebula, atoms are very far from each other, and it takes them a long time to recombine and to be ionized, and all of this process is just very slow. So they do get to emit a lot of photons in this specific line that at the time looked like it didn't even exist. But if we think about this, as I've explained it so far, and we have this shell and everything is being emitted in the O3, we would expect nebula to be, like Huggins said, monochromatic. And we do have some very monochromatic nebula. We would expect them to be slightly spherical as well. And we do have some examples of that. We have Abel 39, which is an incredibly round planetary nebula. It looks bluish here, but that is just a fake color. It is mostly oxygen 3 that we're seeing. And we have the Lemon Slice Nebula, which is my favorite planetary nebula because I think it is the most aptly named of them all. I think the pseudo-coloring in this one is a lot closer to reality because the oxygen 3 line, that is the brightest in planetary nebulae, is in very much the zone of the green. So I don't know if this maybe should be the Lime Slice Nebula. But we would expect all nebula to look like this. And we know that they don't, because when you look for pictures of planetary nebulae, it's kind of hard to find this ones because they are kind of boring. We tend to find things like this. So this brings me to our question number 3 in the poll, which is, what do you think is influencing the shapes and structures of these planetary nebulae? Think about how these are low mass stars like our sun, so they share a lot of things in common with it, and they are just covered by this really, really big envelope. So I'll give you a second. I'm sure you will know the answer to this one as well.
Yeah, it's very interesting, Anna. You know, this is really beautiful what you're saying there about the history. You know what I find so interesting, because I did quite a lot of spectroscopy, is it's definitely true. It's very difficult to replicate these type of very low densities on Earth, because you're talking maybe about 1,000 to 10,000 particles per cubic centimeter in a planetary nebula, which is really low, and it's very difficult. It must have been incredible for people to realize when they saw these so-called forbidden lines from metastable states that this was something different. You know, it takes quite a genius to recognize that it is based on non-collision in planetary nebula. You know, I admire that. I read the history on this, and yeah, it's a really beautiful story. Yeah.
Yeah, I like forbidden lines. I think they are a good sign of how we can actually get so much more out of. I think sometimes when people think about studying space, it looks like we're studying things that are not connected to us at all. But we do live in space, and there are a lot of things that we cannot. I mean, it's the greatest lab that we have. Like, there are so many things that we can never do on Earth.
Yes. And you're going to have a job for a long time because there's so many things we don't understand. Anyway, I'm going to share this now. Okay, here we go.
Okay, good. So the star's magnetic field is a very complicated part of the answer. It is not the main thing that drives the shapes and structures, but to be honest, there are many planetary nebulae that have really weird shapes that can only be explained by magnetic fields. In general, we tend to say that the shapes and structures, like how planetary nebulae will come to have their shape, the answer tends to be winds and pulsations. So all of this process that the nebula was going through, where the core is still warm and it's just sending out photons, that tends to shape the nebulae into things that are not spheres. However, things like the Butterfly Nebula or Hubble 12, which I think should be called the Hourglass Nebula, but no one asked me, and I think there's another Hourglass Nebula. In this nebula, we think that they are very peculiar things happening, and they seem to be different nebula by nebula. So Hubble 12 seems to have the two poles that it has seem to be made out of just rings that are concentric and keep going up. So what people think about is that this may be a case of a ring of dust around the star. So when the star is trying to expand its envelope in this, like in all directions, there's a lot of dust around the star that is pushing the envelope to make this weird shape. That's very much an explanation that is being bounced around. But for most of the cases of nebula where we have sort of two bipoles, we seem to be reaching the conclusion that it might be binary stars. So we might have two stars that are orbiting each other inside of this nebula. Maybe one of them is a planetary nebulae and the other is a different star that is maybe not shining anymore, but it is affecting the gravity around the envelope. That seems to be also a possibility. We also have, to me, weirder shapes like the hourglass nebula, which I think looks less like an hourglass than the one before. But the hourglass nebula is a good case of a nebula where my very simple explanation of us just having hydrogen and having sort of homogeneous envelopes kind of goes to the garbage, because in the hourglass nebula we find a lot of other elements. And we know that we find other elements because when we look at it, it is just not monochromatic. So what's happening here is that because stars are formed, they are mainly made of hydrogen, but there are other materials in this interstellar medium that will come into play. Then we'll have different temperatures in the shells that get formed, and this is going to cause different elements to emit at different wavelengths and will cause the envelope to be shaped in different ways. The main reason that people care about planetary nebulae, outside of them being really pretty to look at, is that they enrich the interstellar medium. So all of these heavy elements that they form and all of the materials that are formed in their envelopes throughout all of this time where the atoms have time to be made into molecules and so on, these are all released into the medium that surrounds them. So eventually the envelopes around a planetary nebulae will fade away. This material will just join the medium around it and be part of the next generation of stars. And we're going to have a very hot central star that is just hot because it's holding on to its thermal energy, but its thermal energy is slowly running out because it's emitting photons, and the envelope will slowly start to become more and more transparent to us. So eventually this will become super faint, and we will for some time be only able to see a hot central star. We have a good example of that in our night sky, which is Sirius B. That's a hot central star of a planetary nebulae, or as we know them, a white dwarf. And the white dwarf has no reason to keep on heating up. It's just cooling down, cooling down. It will become lukewarm, and the less hot it is, the fainter it will be. So eventually white dwarfs will just be cold stars that we will not be able to see because they will just not be emitting anything. That is, of course, everything I've told you so far. Like I said at the start, we're always when we talk about stellar evolution, we tend to talk about a single star. And we know that stars are usually not just born in isolation. Stars are mostly born in clusters. So there's a lot of binaries, and binaries will have, like being in a binary system will impact the evolution of a star. But for simplicity, we try to understand the path of a single star, and then other people will try to think of how this interacts with binaries, and it will explain a lot of what we see in the weirdly shaped nebulae. So to wrap it up, we'll quickly go back to stellar evolution because we know that this is not the end for all stars, but I'll just summarize it. So we have two main paths for stellar evolution. High mass stars will be red supergiants and then will explode. Our low mass stars will have much quieter life. We'll go through a red giant phase, and then we'll slowly turn into the planetary nebulae. And the lengths that this, the time that this processes take is enormously different. So as I said, very massive stars will take like 20-something million years, and then they'll be gone. Whereas a star like our sun will spend around 10 billion years just doing hydrogen into helium in its core. Then it'll spend around a billion or so years as a red giant, and planetary nebulae tend to last around 10,000 years, which is a lot longer than the few months that supernovae can last in the sky. Once this is done, we once again have mass come into play. So if our high mass star was very, very massive, this core, after the supernova explodes, we have a core that has way too much mass. So the gravity that is trying to make it collapse is much larger than what the electron degeneracy could ever do to make it stop. So gravity will win and we'll have a black hole. If it's not that massive, then what's going to happen is that we're probably going to fuse our protons into neutrons, and the neutrons will once again have the degeneracy pressure. So that's going to stop the star from collapsing. In the case of our planetary nebulae, as I said, the nebula, the envelope, will slowly fade away and we'll be left with a white dwarf that will probably survive for quite some time because the electrons that are inside of it will stop it from collapsing, even when gravity really wants it to collapse. So that is going to be the end of the life of most of our stars, and that is also the end of my talk. So I hope you learned, and I will take any questions.
Thank you so much, Anna. We have one more poll. Do you want to launch that? I think it's this one. What a planetary nebula. You forgot that one, but I'll just launch that for you.
I hope we'll get good answers on this one. This is the test to see if you've been paying attention.
Yes, exactly. Yeah, and you can stop sharing, please. And then we got lots of questions, and that's fine. First of all, Dr. Ennis, thank you so much. What a brilliant talk. Very inspiring and really beautiful as a lecture. Really, it's such an interesting subject. And before I go to the audience, all of us at iTelescope, we love taking planetary nebula because it's so beautiful. And I have a very simple question for you, actually. So when you look at, you mentioned the hourglass nebula, the butterfly nebula, the helix, the ring, gosh, it just goes on and on. I think we have about 1,000 or 2,000 nebula in our own galaxy, somewhere around that, right? That we know. Why do we understand really? I mean, you're talking a lot about the spectrum, but apart from the spectrum, just the explosion, the shock waves. Do we really understand why they look the way they do? Is that well understood, or why are they so different?
Well, I mean, so it is very much an ongoing a topic of research because there are so many nebulae, and they all there's some types that we understand better. I think nebulae like the butterfly nebulae, where we have sort of like what they call like bipoles of emission. We are pretty sure that those are binary stars that are in there. So it may be a white dwarf that is orbiting this other white dwarf. One of them is still in its planetary nebula phase, and the other one has just kind of faded away. We understand the dynamics of how that could shape the envelope. We know that for the most part, it tends to be the variety of elements that we see. And when you look at the spectra of all of these nebulae, you can really see that, like the emission lines, it is like people usually talk about oxygen 3 because it's the brightest and the most iconic one, and we discovered oxygen 3 because of them. But there's a lot of other bright emission lines that you can find, and different emission lines means you have different elements, and different elements will be doing different things according to their temperature and how they can combine with the others. So that tends to be the cause. Mm-hmm. There's a lot of shapes that we don't really understand yet.
Okay. So, for example, do you have an example? Just curious.
I don't have any at hand right now. Okay. But I mostly thought about the ones that we do understand because the other ones are complicated.
Right.
I study extragalactic nebulae. So to me, planetary nebulae are little dots. Like we cannot really see their shape.
Right.
I care more about how many there are in other galaxies, how fast they move, things like that. But yeah.
Okay, I'm going to jump. Thank you so much. I'm going to jump straight to the questions. And first of all, there's so much praise in the audience, which I want to pass on. Thank you so much for a kind audience and really such a beautiful talk. So I'm going to jump now to the questions and answers. So Eric comes with the first question. Why does contraction of the core cause expansion of the outer layer?
Well, that's a hard question.
Yeah.
So it's a physical fact that we know empirically. It's called the mirror effect. I don't really I don't think I can explain the physics of it very well. So I will put a pin on that one
Okay.
because it's not very much it's not my area.
Right.
And I don't want to tell you something that is not
That's
entirely true.
that's that's perfectly okay. Thank you. Don't worry. That's fine.
Sorry, Eric.
And Steve comes with an interesting one about protostars and the Hale-Bopp object, which are shock waves, right? Shock waves that we can see. So are protostars the same as Hale-Bopp objects as shown in images?
Oh, well, yes. So there's a lot of there's different types of protostars, and it is because they're kind of hard to detect. A lot of the times people will have different names, like they'll have different names. They're talking about the same object, but what they're describing is the way that we detect them, where we detect them, and things like that. But they're basically like T-Tauri stars are also protostars, and some people will get very mad at you if you call them T-Tauri stars because they are the definition of when a star becomes a star is
Huh.
kind of blurry. But yes, they're all basically just protostars. It's a
Okay,
very broad definition.
that's a good question. Thank you. Okay, next one. I assume is what is the frequency of these thermal pulses or the wavelength or the shock waves, or that's what he's talking about, I think, Mike.
Yeah. Okay. So that depends a lot. There's not AGV stars are very different. Like between there's a variety of what AGV stars can look like. This is it's not a very they're not short frequency processes, right? So this thermal pulses will take at the minimum, like you've seen Betelgeuse, you've seen sort of novae type of stars. It's not like they're seconds long, but it really depends on how hot the star is, how massive it is, at what point it is in the fusing of the shells. So there's a lot of things that make it really hard to give you like a number for that because they're not very well constrained.
Okay, thank you. And Max, I'll just have to give you a little bit of background who Max Whitby is. He's quite a star in the truest sense. So, Max has written this beautiful book called The Visible Universe, which, by the way, Max, I have nearly given away all my copies. Otherwise, I would show it to you. I have the one hand signed from you. So, it's a beautiful, if you really want to have an incredibly beautiful astrophotography, yeah, modern book, then take Max Whitby's and Charles Bracken's book called The Visible Universe. And his question, of course, is very much to what you see, right? So he says, great lecture, thank you. We would all agree with that. For astrophotography, which targets do you think are the most interesting to image with a nitrogen emission filter, right? So that's a good one. That's a very good question. I don't know if you know the answer, if you've done anything
So
with that.
with the that's a very hard question.
Yes.
Hmm. Okay, so planetary nebulae do tend to have emission in the nitrogen um, line, so it's not very hard to find nebulae. Um, I don't know. Like I said, like I mostly deal in extragalactic ones, so my I don't know the specifics of the Milky Way ones, but I don't think it should be a problem because it is very common for planetary nebulae to emit as well in nitrogen. They're not super bright, but I think you can get good pictures. Planetary nebulae are very good objects to look at if you are doing astrophotography. If you look at them in different emission filters and you make what you call it, like a multicolor image, combining all of your like very narrow band filters, you'll get amazing structures because that is where you can really see all of these weird shapes. It will come from just trying out all of the different elements and seeing where the nebula is emitting. I think nitrogen is a very good one to do for nebulae.
Good, thank you. Very nice. Okay, Stefan from Denmark, Copenhagen, here. Here we go. Do you know if the star surface becomes structured with hexagonal patterns when convection flows are present? Interesting question. Wow.
Oh,
This,
that's
yeah,
that's a lot of physics.
it
Uh, I
is. It is.
I don't know the answer to that. I think so. Convection
Mhm.
is a very big part of what happens, especially for AGB stars. Convection is super important, and we think we understand convection, but kind of like up to a point. I think we understand convection a lot better in like regular physics, like Earth-based physics.
Yes.
Convection in stars has proven challenging, and there are some things that we don't really know how to model. So I'm sure there are works on this, but there is like a very big field of people who look at the surface of stars and try to understand their shapes, which is hard because we cannot actually see 3D versions of the stars. We will only just kind of be limited to seeing one dot. So I don't know exactly, but convection is complicated.
It is, but I mean, Stephen may be referring to the sun, of course, also where this has been studied, right? So, um,
Yeah, well, but the sun is very much still a main sequence star, so we're not really dealing with it's a different there's different mechanisms at play when you have the core still working away at its nuclear fusion.
okay, thank you, and thanks, Stefan. Okay, next question, Richard. One of the survey questions was shape. Could gravity waves be a consideration? Which question?
Uh, I think the scales at which gravitational waves do affect everything
Mhm.
and everyone all at once. However, the scales at which that can be considered relevant are a lot larger. Like even when people look at the scale of something like the solar system, gravitational waves don't really, even though they have some effect, the effect is so minor that we cannot really see it. And planetary nebulae are like they're large, but at no point are they larger than the solar system. So I don't think the effects of gravitational waves are too important in these shapes.
Okay, good. And Stefan again, are brown dwarfs expected to follow the low mass star evolution? Ah, okay.
Well, brown dwarfs, as far as I understand, I think most of the types, like most other stars that we call something dwarf, are stars that never started doing nuclear fusion in their core. So brown dwarfs, if I am not mistaken, and I could be because there's a lot of dwarfs, but I'm pretty sure brown dwarfs are stars that start off as our sun, but they don't really have enough mass. So they're kind of between Jupiter and the lowest mass star that we can think of. Like they have more mass than a planet, but not enough that they can start fusing hydrogen into helium. So technically, they're not even stars at any point because they don't really shine because of nuclear fusion at any point.
Okay. Okay, good. George, you still have energy, Anna. You still have energy for a few more.
Yes, yes, I have time. I have time.
I don't want to take too much of your time. Aren't elements heavier than oxygen also found in the supernova event? Sorry, event. Yes.
Yes. So the question that we had in the poll very specifically means elements that are formed in the core of stars. So through nuclear fusion, we can make it to iron and then we're done. But we know that heavier elements are also formed in the stars somehow. Supernovae are one of the big sources of heavier elements. There's also collisions of stars. So neutron stars that collide are also a big source of heavier elements that we don't really know where else they would come from. Um, so yes, supernovae do form heavier elements. It's just not through nuclear fusion in the core.
But I think that's a very good educational question just to clarify that, right? So people think, why would we stop at iron, right? So it's thank you for that point. Giolamo says, can you please explain why the convective envelope of the AGB phase becomes radiative in the post-AGB phase? Thank you.
Yes. So in order to have convection, we need to have a steep gradient in the hotness of the envelope. So we need some parts of the envelope to be really hot and some to be really cold, because convection works through taking the hotter things up to the surface, and the cooler things go down, and then they get heated up a little bit, and then this keeps happening. So what happens through convection is that eventually heat gets distributed evenly. And once heat gets distributed evenly, we don't have a gradient in temperature anymore. So convection cannot work because there's not a very hot part of the material that it can pull up to the surface. Everything is kind of the same amount of hot. So then convection kind of has to stop because there's nothing else for it to do.
Okay, thank you. Hi, Sikander, nice to see you. Yeah, Sikander's another. He's also, he's got a very nice telescope in Chile, by the way, T73, I think it is. And it's on a network, and he's doing a lot of imaging at the moment. So that's where his question's coming from. What are the thoughts on the jumbos recently found in the Orion Nebula by the JWST? Do you know that? I'm sure.
On the
Yeah,
jumbos.
on the jumbos. I would have to look that up too. I don't know.
I'm not really sure, but if you want to tell, okay, let me think. Okay, so I think they are they're Jupiter mass things, right? Like they're objects. Okay, I am Googling this because I did not remember what a jumbo was.
Take your time.
But yes, okay. So it is. I wish I knew. If I knew, I could write a paper on this. Yeah, okay. So binary Jupiters. That was I was not super sure, but it is complicated because what we understand of how planets are formed very much follows this path of stellar evolution that we've come to, right? Like when we have this accretion disk that is making the star, this accretion disk will basically just fall apart at different places, and it will make planetesimals that will then turn into planets. So we do associate planetary formation very much to the early stages, and then we assume that as the star goes through the red giant phase, most of the planets will be destroyed or absorbed. So it is really weird for an object like a planetary nebulae to come up with this many, not only Jupiter-sized planets, but also binary Jupiter-sized planets. It is very weird, and it's also weird that we've only seen it once. And I think the best answer I can give you is that, like everything in astronomy, when we find something once, I will hold judgment on it until we find it at least 3 times. Like once, I would need to look at the data, and maybe like there are things that will just happen in like very, very rare things. But I do think with JWST, we can really look at a lot of this planetary nebulae. I mean, you've seen the Hubble images are amazing, but JWST is not only going to give us better resolution, but it's also going to let us look at nebulae through the infrared. So if they have dust around them, like we saw in the Butterfly Nebula, then we can actually probe the dust and see what's happening inside of it. So I think that is the way forward to try to understand where all of this 40 binary, geez, that's a lot of binary Jupiters. But yeah, I really don't deal in exoplanet formation, but I think this is puzzling everyone that does.
Very interesting topic. Thanks, Sikander, for bringing that up. Natalia, thanks also for putting the clarifications in there.
Yes.
About, yeah, I'm just seeing her clarification. Thank you very much. So she says, thanks for the great talk. We all agree with that. Is it possible to predict somehow the shape of a future planetary nebula or supernova remnant before the explosion? That goes a little bit into what I was asking. Though I do realize that it is extremely difficult to check such predictions. Yes.
So. Yeah, well, for planetary nebulae, it's kind of impossible to check if you predict that because of just how long we are alive for. Yeah. But it is, so we can probably predict some things, especially for supernova remnants. We can look at a star when it's a star like Betelgeuse. We can look at its mass, and we can look at its temperature. We can look at its environment and see if there's dust around it. So that can help us figure out what a supernova remnant will look like up to some extent. With planetary nebulae, we can look at a red giant star, and if we can probe its atmosphere and we can get some sense of the elements and we can look at the environment, we can get some idea of what colors we're going to see, if there's going to be a bipolar sort of envelope. I think those things could potentially be predicted. Because it is kind of impossible to check those predictions, I don't think anyone works on doing that.
Right, right, right. Okay. Lots of interesting research topics are coming up here. Okay, Brian is asking, is there a stage that exists? Here we go again. Between AGB and post-AGB, and what is the estimated length of time between each of these stages prior to the star's death or lifespan?
So, well, AGB sort of leads into post-AGB, but whenever we talk about like the stages of a star's life, when we talk about nuclear fusion stages, we can see the start and the end in a clear way, because nuclear fusion starts and then stops. When we look at stages like the AGB or the post-AGB, where we're doing shell burning and we're considering like the what's happening in the envelope, it is very much sort of like a continuum, right? Like you don't say, okay, the star one day stops being an AGB. There's nothing in between, in the sense that astronomers have not classified the process into smaller stages. AGVs will just like, we consider that when the envelope stops being convective and starts being radiative, we call it a post-AGV instead of an AGV. But even saying at which point a post-AGV star starts being a planetary nebulae is kind of a blurry line. Like we think when a post-AGV star stops burning in shells, we say it's a planetary nebulae. But from where we are and what we observe, it's very hard to find like there's a lot of overlap between all of these stages. What is, sorry, I'm reading the second part of the question. Yes. What is the estimated length? Okay, and these are pretty long stages. These are stages that take up to like 1 billion of years. They are similar to, they're shorter than the red giant, I think, but they are kind of comparable to a red giant phase. So they are about like 1 billion years or so.
Okay, thank you. And Stefan, who comes as an experimental physicist, here we go. So he's talking about nitrogen in planetary nebula. Can you determine the ratio of N14 to N15? And would it be the same as on Earth?
That is a very technical question.
Yes, it is.
That I don't think I know the answer to that one, okay. Because I don't think, so I usually, the thing is, so when we think about looking at the spectrum of stars, there's a lot of lines that are there, but they're not very bright. So yes. It's hard to see a lot of these other lines. And also we're kind of limited by what telescopes we use, right? Because our telescopes, unlike on Earth, where we can kind of look at different wavelength ranges more easily, when we look at stars, if they're far away from us, things are redshifted. So we're kind of limited in what we can look at. But I don't have an answer to that one.
But Stefan, maybe you can find it out from your backyard, because I know he's got a spectrograph on his telescope.
Yeah, let me know if you
hear that one out. You can find the answer and tell us. Thank you for the question. Okay, Paolo is saying an easy question. Oh, well, they're never easy questions. So that's always the worst part if someone says this is easy. Okay.
Yeah.
Do you have recommended links to documentation about stellar evolution? Okay.
Oh, documented. Okay. That's a hard question, actually.
I knew it.
Honestly, like I haven't really watched a lot of documentaries about astronomy. I watched Cosmos, the Carl Sagan version, and that I feel like that is the thing that I've gone back to the most in life. I think in his book, I know this is like a very simple rec for astronomy fans, but I have Cosmos by my bedside table, and I think even though like it's kind of old, his explanations on stellar evolution are like the easiest to follow, and they're still pretty much the most accurate. I don't have other good recs. I'm sorry.
That's okay, thank you. But that's something we can surely look up. Okay, thanks. Gerhard, and we're almost at the end now. Is your presentation? Yeah, in your presentation we saw that the white dwarf Sirius B. Yes, did it have a kind of planetary nebula, or was Sirius A too strong to prevent it? Oh, okay.
That's a very good question. So I would assume that my understanding is that Sirius B had a planetary nebulae, and we are looking at like the white dwarf that is still hot, but the planetary nebulae has faded away. We have no real way of checking that I can think of. And it is also true that, like I said, like when we have binary systems, weird things happen. And
Hmm.
Sirius A is a big star. So I am sure that something gravitationally could have happened. I don't think it could have prevented it from having a planetary nebulae. Um, but I am sure it must have had a funny shape, because they cannot escape having a funny shape when they are in a binary system.
Okay, thank you. And finally, about the famous Bock globules, those black things, right? Can they be considered as protostars? Hmm.
Well, I think bug globals are, so they're regions where they're star formation, right? So we have, I think we have protostars in bug globules, but it's not. I don't think bug globule. I am. It's a tongue twister. I don't
Yeah.
think bug globules are uh, then condensed into one protostar, right? Like they are mostly star forming regions. So there's maybe a couple of them. They're inside H2 regions, right? So if
Right.
I'm not mistaken, I think they have two oppositions to them being called protostars. But honestly, the protostar definition is very vague. So you can probably call whatever you want a protostar. But I think Bok globules don't necessarily collide into just one star, and they don't always form stars.
Yes. Okay.
So I wouldn't say they're protostars in that sense.
Thank you. That was not easy. I hope it was okay. We bombarded you with lots of quite challenging questions. We have a very knowledgeable audience, and we have a
Yes.
very knowledgeable speaker. Thank you so much, Dr. Anna Ennis, for this really marvelous and very inspiring talk. So thank you, and thank you to our audience for all the questions and your enthusiasm and participation, which makes this so special. I think we are the only ones who give talks like that and also give a lot of chances for audiences actually to ask questions. And we're going to continue next week. It's going to be very interesting. We're going to into the geology of exoplanets and our own planets that we have, and what the geology means for possible life. So very inspiring. It's something that we had to shift from last week, so it's going to be next Friday. So do attend again with all your questions. I think it's going to be another inspiring talk. On that note, I wish everyone a wonderful weekend. Thank you again, Dr. Ennis, and all the best. See you soon. Thank you.
Thank you.